Canadian airspace, 24th January 1978, 11:53 GMT. A Soviet satellite carrying a nuclear reactor working on uranium, enriched with isotope uranium-235, re-enters the atmosphere over the North Pacific, crosses into Canadian airspace, and breaks apart. Debris deposits across Canadian territory, unannounced, uncontrolled, and unmapped. The contrast is immediate and documented. Moscow's assurances emphasize design, intent, and safe orbital disposal, yet Canada's first operational reality is practical and measurable. Locate fragments, recover radioactive material, and test debris before members of the public encounter it. Within minutes, the United States offers technical assistance. Canada accepts. The question driving what follows is not speculative, it is procedural. What happens when a nuclear system meant to stay in space comes back down without warning, and the only containment is an emergency search grid stretched across winter terrain? The answer will be written in detector counts, flight hours, and treaty clauses. 18 September 1977. Baikonur Cosmodrome. A launch notification enters international tracking channels, and monitoring begins almost immediately. The payload is not routine. It is a radar ocean reconnaissance satellite, a RORSAT, whose power source changes the risk model if anything goes wrong. The operational expectation is clear and documented. The reactor enables continuous active radar surveillance of naval targets. Then, at end of mission life, the hazardous core should be kept away from Earth by orbital boost maneuvers rather than atmospheric destruction. The safety concept depends on controllability. Soviet designers selected nuclear power because active radar requires steady electrical output that solar panels in low orbit cannot reliably provide without prohibitive size and drag penalties. Low orbit improves radar geometry, closer range, better resolution, reduced detection delays, but increases atmospheric drag and accelerates natural orbital decay. The trade-off is explicit: operational advantage in exchange for a recurring end-of-life disposal requirement. Each RORSAT mission must execute a final maneuver, boosting the reactor into a higher graveyard orbit, where radioactive decay can proceed over centuries without re-entry risk. The European Space Agency's technical summary later documented the disposal strategy in precise terms. Most reactor cores were successfully elevated to orbits between 900 and 950 kilometers altitude, well above the operational zone. The system worked as designed most of the time, but the documentary record also frames the central failure mode clearly, losing spacecraft control before disposal procedures can be executed. This is a systems problem, not a rumour problem, and not a weather problem. In the Canadian government's later filing under international liability conventions, the baseline fact is stated without embellishment. The object was placed in orbit on 18 September 1977, and it carried a nuclear reactor. Cause leads to effect with mechanical clarity. By choosing low orbit plus nuclear power, the program accepts that any loss of control is no longer a space systems problem alone. It becomes an international radiological response problem. 2 satellites failed the disposal maneuver. Kosmos 954 was one of them. The reactor aboard Kosmos 954 was a BES-5, also known by its Western designation as Book. The schematic is compact and functional. Uranium-235 fuel rods surrounded by a beryllium reflector, controlled by rotating drums that modulate neutron economy, coupled to thermoelectric converters that turn decay heat into electrical current. No moving coolant, no turbines, just solid-state energy conversion. The design reflects its purpose: provide kilowatts of continuous power in the vacuum of space, survive launch vibration and thermal cycling, and operate autonomously for months. The expectation, documented in Soviet technical notes provided to Canada after the incident, was straightforward. The reactor's design provided for its transfer into a storage orbit and total destruction of the reactor's active zone after entry into dense atmospheric layers. Reality, as Canada's recovery teams would document, told a different story. If disposal fails, the reactor becomes a terrestrial contamination source, not a distant engineering abstraction, but physical debris carrying isotopes with half-lives measured in years and centuries. Western analysts, working from intelligence photography and recovered fragments, reconstructed the hardware. The reactor was not large by terrestrial standards, perhaps 50 kilograms of enriched uranium, a beryllium reflector assembly, control mechanisms, and structural supports. But every component carried activation products and fission residue from months of operation in orbit. Understanding the schematic clarifies why debris would later be described not as a single object, but as plates, rods, and components, scattered across hundreds of kilometers. The safety story, therefore, is not about reactor operation in space. Soviet RORSATs operated dozens of reactor cores without incident in orbit. The safety story is about what happens when the disposal step, the orbit raise, does not occur. When that maneuver fails, the reactor's fate shifts from controlled decay in a graveyard orbit to uncontrolled re-entry and fragmentation. The graveyard orbit is a time-buying tactic, not containment. The principle is simple. Boost the reactor high enough that atmospheric drag becomes negligible, allowing radioactive isotopes to decay over centuries before the orbit naturally deteriorates and re-entry occurs. At 900 to 950 kilometers altitude, the timescale stretches from months to millennia. The strategy delays the problem until it is no longer a problem. But execution requires functioning systems at the end of mission life. Attitude control must orient the spacecraft correctly. Propulsion must deliver the velocity change. Electrical power must support the maneuver. Telemetry must confirm success. Any single failure in this chain means the disposal does not happen, and atmospheric drag resumes control of the timeline. The European Space Agency excerpt is precise and unforgiving. Disposal orbits were mostly 900 to 950 kilometers, and Kosmos 954 failed execution. The satellite remained in its operational orbit, low, decaying, and increasingly unpredictable. Tracking stations worldwide began plotting its position multiple times per day, calculating how atmospheric density variations and solar activity would affect drag, and therefore re-entry timing. Policy and engineering converge on a single question. If the boost does not occur, when does the reactor come down, and where? Prediction accuracy depends on factors that cannot be perfectly known. Spacecraft tumbling rates, atmospheric density fluctuations at altitude, the satellite's ballistic coefficient after potential breakup. The question shifts from if to when, and then to where within a swath thousands of kilometers long. By mid-December 1977, analysts in Washington and allied capitals understood that Kosmos 954 was not behaving predictably. The orbit was decaying. Disposal had not occurred. The timeline was shrinking, and prediction windows were tightening. Public messaging and response coordination were becoming the next battleground, because the physics of re-entry was now driving diplomatic and operational decisions on a schedule measured in weeks, then days, then hours. Mid-December 1977, North American Aerospace Defense Command tracking facilities. The orbital behavior of Kosmos 954 no longer matches the expected profile for a satellite executing end-of-life disposal. Instead, analysts observe steady altitude loss, classic atmospheric drag signatures, and attitude instability that complicates prediction models. The expectation was a controlled boost to graveyard orbit. The reality is systems degradation before disposal, leaving the orbit increasingly uncertain. Prediction windows, initially spanning days and hemispheres, begin to tighten as re-entry approaches. Each new tracking path refines the estimate, but variability in atmospheric drag and spacecraft tumbling means the impact footprint remains a probability distribution, not a point. A declassified government account captures the operational tension in plain language. Even 16 hours before re-entry, interagency groups are still debating what to say publicly, because uncertainty in timing and location prevents definitive statements. The passage describes meetings, phone calls, and message traffic as officials try to balance the need to warn populations against the risk of causing panic over an event whose consequences are not yet measurable. The technical constraint is unyielding. Orbital mechanics and atmospheric physics provide probabilities, not certainties. Analysts can say the satellite will re-enter within a specific window and along a general ground track, but not which orbit pass will be the final one. This uncertainty drives every downstream decision. where to pre-position response teams, which governments to notify, when to issue public statements, and what those statements should say. Cause and effect link tightly. Prediction uncertainty forces diplomacy, and response coordination into reactive postures. Equipment can be staged, but deployment cannot finalize until re-entry occurs and debris locations are confirmed. Communications between agencies and governments accelerate. Following the shrinking timeline, the declassified narrative notes calls at 0500 hours announcing imminent re-entry, officials working through the night, and logistical preparations proceeding in parallel with diplomatic contacts. By late January, the question is no longer whether Kosmos 954 will re-enter, but when and where, and whether anyone will have enough warning to do anything about it. 23 to 24 January 1978. Washington Response Coordination Centers. The final hours before re-entry are marked not by calm, ordered procedures, but by communication friction and the pressure of compressed timelines. Phones ring in secure facilities. Maps are updated with each new tracking solution. Critic-level messages, communications reserved for events of immediate national security significance, move between agencies. The expectation in contingency planning was a clean interagency process with clear lines of authority and responsibility. The reality, documented in declassified accounts, involves misrouted messages, access delays at secured facilities, and the hard truth that even well-designed procedures struggle when execution windows shrink to hours. Badge gates slow responders. Notification chains encounter gaps. Uncertainty compounds as officials try to determine not just where the satellite is, but where it will be and what should be communicated to the public. At 0653 Eastern Standard Time, the satellite is down in Canada. The notification arrives after the fact, not before. The declassified author perspective, an official involved in the response, describes the sequence with frustration barely concealed in bureaucratic language. The event moved faster than the communication system could fully support. Time systems matter, and the account clarifies them once. The narrative uses Eastern Standard Time for US-based actions, but re-entry itself is recorded in Greenwich Mean Time, 11:53 GMT, to align with international tracking standards. This is not a trivial detail. When multiple governments, time zones, and tracking networks must coordinate, every hour marker must be unambiguous. Cause and effect. Communications friction affects how quickly technical support teams are mobilized and how governments frame risk to their publics. Canada learns of the re-entry rapidly, but the Soviet Union's notification to Canada comes late and lacks the detail needed for immediate response planning. The Canadian government's later filing records bluntly that urgent questions posed to the Soviet ambassador on 24 January received incomplete answers, and that fuller technical details, reactor design, isotope inventory, breakup predictions, arrived only after the search was already underway. The decisive question crystallizes: where did Kosmos 954 come down, really, and what survived re-entry? 24 January 1978. Canadian airspace over the North Pacific and Western Canadian territories. Canada's official claim under international liability law records the key fact with precision. At approximately 11:53 anti-meridium Greenwich Mean Time, the satellite entered the atmosphere north of the Queen Charlotte Islands, broke apart during re-entry, and deposited debris across Canadian territory. The expectation embedded in popular understanding, and even some technical optimism, was that re-entry heating would destroy the reactor, reducing it to vapor or small particles that would disperse harmlessly. The operational reality was different and immediately measurable. Fragments persisted, and the search area expanded from a theoretical point to a documented corridor. Health Canada's later technical summary describes radioactivity scattered across 124,000 square kilometres, an area larger than many countries. The breakup did not produce a single impact crater. It produced a debris field stretching from the Northwest Territories into northern Saskatchewan, with fragments distributed along the satellite's final orbital ground track. Why does breakup spread risk instead of eliminating it? Aerodynamic heating during re-entry affects different materials differently. Low-density components and thin structures burn up or fragment into particles. High-density, refractory materials, reactor fuel, beryllium reflectors, structural supports, can survive to lower altitudes and reach the ground as discrete objects. The fragmentation process is violent and chaotic, scattering debris across hundreds of kilometers as the satellite tumbles and disintegrates. Canada's immediate operational requirement shifts. The response is no longer confirm burn-up and reassure the public. It becomes locate debris, measure radiation levels, recover hazardous fragments, and protect public health. Within minutes of re-entry confirmation, the United States offers technical and material assistance, radiation detection equipment, aircraft, and specialist teams. Canada accepts immediately, and joint operations planning begins the same day. The Canadian claim documents an additional procedural problem. A senior external affairs official presses the Soviet ambassador for urgent, precise technical details and expresses surprise at the lack of prior notification. No advance warning was provided, despite the satellite's deteriorating orbit being observable for weeks. If the debris footprint is 124,000 square kilometers, detection and recovery become the first limiting factors. How do you find the fragments that matter? Evening of 24 January through early 25 January 1978, Edmonton, Alberta, and the Great Slave Lake region. The Operation Morning Light Report, Canada's official account of the search and recovery, documents how the initial search zone is defined. Tracking data provides a predicted impact corridor. Eyewitness accounts from residents in the Great Slave Lake area who observed the satellite's luminous re-entry pass provide a gross check against model output. Together, these inputs bound the search area, though uncertainties remain large. The expectation in pre-re-entry planning was that ground teams could search locally once the impact zone was narrowed. The reality forces an airborne first doctrine. The footprint is too large, the terrain too remote, and winter conditions too severe for ground teams to survey efficiently without guidance. A United States task force arrives in Edmonton around 1930 hours Eastern Standard Time on 24 January and immediately begins installing radiation detection equipment into Canadian Forces aircraft. The integration is rapid: specialist detectors, data recording systems, navigation aids, because the search cannot wait for perfect preparation. The first dedicated airborne search launches at 03:15 Eastern Standard Time on 25 January. A C-130 Hercules transport flies a long, straight-line search from Yellowknife to Baker Lake, covering more than 500 miles along the projected debris corridor. The aircraft carries gamma-ray spectrometers and scintillation detectors, instruments capable of sensing radiation anomalies above natural background from altitude. The Operation Morning Light Report states the initial goal clearly: search the entire 15,000 square mile area. Later, as airborne surveys identify specific radiometric hits, the search concentrates on verified anomalies rather than continuing broad area sweeps indefinitely. Scale drives everything else: fuel requirements, crew rotations, detector calibration, data processing, and how quickly the public can be reassured or warned. The search grid design determines where helicopters will verify airborne signals, where ground teams will be deployed, and which areas can be declared clear based on negative survey results. The first flights do not solve the event. They define where the next phase of the response must focus: helicopter close-in verification, ground recovery, and laboratory analysis of whatever is out there, waiting, in the snow. 26 January to 12 February 1978. Canadian Forces Base Edmonton, Hangar 5. The Operation Morning Light Report documents a decision that shapes public perception and operational accountability. Press conferences will be held daily at 10 antimeridiem, starting 26 January and continuing until 12 February. These briefings are not optional public relations exercises. They are a structured response to global media attention and domestic public concern. The expectation in any classified or sensitive operation is controlled messaging: release only what is confirmed, avoid speculation, protect operational details. The reality is that operational secrecy becomes incompatible with public concern once the story of a nuclear satellite crash spreads worldwide. The response must demonstrate transparency and process, without claiming certainty that does not yet exist. The technical workflow for building confidence is documented in a process diagram titled Kosmos 954 assessment. It shows how uncertainty is reduced step by step. Airborne acquisition of radiometric signals, computer analysis of detector data, re-entry trajectory calculations, ground-based measurements of recovered debris, laboratory spectrometry and isotope identification, and finally, recovery and transportation under radiological controls. Each step feeds the next. Each step can be explained to the press as evidence of methodical, science-based decision-making. Technical task lists from the national laboratories involved, Sandia, Livermore and Canada's Whiteshell Nuclear Research Establishment, provide the detailed work breakdown that underpins public statements. The tasks are concrete: trajectory analyses, aerodynamic heating models, reactor design schematics analysis, gamma spectral measurements, beta count rates, particulate size distribution studies. These are not vague assurances. They are measurable activities with results that can be reported. An operations meeting photograph provides a rare, named leadership visual. It shows Colonel David F. Garland, the senior U.S. government representative Marlon E. Gates, and Deputy Troy E. Wade, officials whose names and roles are documented in the historical record, not invented. The report states that press conference statements were followed by question and answer sessions where questions were fielded by technical participants. This format matters. Journalists can probe, experts must answer, and the public record is built in real time. Even with daily briefings, one question remains unanswered until field teams produce hard data. How much hazardous material survived re-entry, and in what form? Large, recoverable pieces or dispersed particles that will require different cleanup strategies? February 1978. Northwest Territories, remote terrain across the debris footprint. The search method is systematic and layered. Airborne gamma-ray surveys from fixed-wing aircraft identify anomalies above background radiation. Helicopters conduct close-in verification flights to confirm signals and mark locations, and ground teams recover debris under radiological safety protocols. The expectation in popular imagination is that debris can be found visually, wreckage scattered on the surface like an aircraft crash. The reality is that detection is primarily radiometric. Many fragments are small, partially buried in snow, or visually indistinguishable from natural objects. The radiation signature is often the only way to locate them. The Operation Morning Light report describes the workflow in procedural language. Airborne anomalies are recorded with position coordinates. Helicopter crews drop colored banners or streamers to mark verified sites, and ground teams navigate to marked locations using handheld detectors and transponder navigation aids. A photograph in the report shows a microwave-ranging transponder, critical logistics infrastructure for relocating precise points in featureless winter terrain where visual landmarks are scarce. This method is designed to keep people away from unknown radiation sources until measured. Crews do not approach debris blindly. Dose rates are estimated first, then approach distances and exposure times are calculated. Time, distance, and shielding, the fundamental principles of radiation protection, are applied in the field, not just in textbooks. But the documentary record also captures a non-technical truth about fieldwork. Not every discovery comes from instruments alone. The report documents that on 28 January 1978, John Maudhorst and Mike Mobley, two men on a local winter expedition in the Thelon River region near Warden's Grove, spot an object in river ice. They report it. The object proves to be a large piece of Kosmos 954 debris. The contrast is immediate. High-altitude tracking and million-dollar aircraft predict a corridor, but local discovery makes it real and raises a new risk. If trained explorers can encounter fragments by chance, so can other residents, trappers, or travelers. The urgency of the search intensifies. One large piece can be found by chance and secured. Hundreds of smaller fragments and dispersed fuel particles cannot. The response must now measure background radiation across the entire footprint and distinguish natural from man-made sources, a much longer and more difficult task. February to March 1978. Search operations expand to multiple town sites and field camps. Snowdrift, Pine Point, Fort Resolution, and temporary encampments established along the debris corridor. Before responders can interpret detector readings, they must establish baselines. The Operation Morning Light report provides the necessary numbers. rare in their precision and clarity. Natural background radiation on land in the search area may be 7 to 10 micro-roentgens per hour. Instruments are sensitive enough to detect an increase of about 2 micro-roentgens per hour at that level, statistically significant but small. Background radiation over frozen lakes is approximately half the land value, 3 to 5 micro-roentgens per hour, because ice and water provide shielding from terrestrial sources like potassium-40 in soil. These numbers define operational thresholds. A reading of 15 micro-roentgens per hour on land might be natural variability or instrument noise. A reading of 50 micro-roentgens per hour is almost certainly man-made contamination and warrants investigation. The expectation in simplified media accounts is often a single crash site that can be fenced and controlled. The documentary record shows scattered distribution instead. The report states bluntly, particles have not been distributed in a dense pattern, but are scattered randomly. Fragments are found far apart, kilometers, sometimes tens of kilometers, making broad public reassurance harder than managing a single fenced perimeter. Cleanup choices are constrained by practicality and population exposure risk. The report notes that cleanup in town sites was feasible, specifically where crowds might gather, schools, community centers, main streets. Cleaning the entire 124,000 square kilometer footprint is neither possible nor necessary. The strategy becomes find and remove high-activity fragments, survey populated areas intensively, and monitor less trafficked zones for residual hazard. Manpower becomes a storyline of its own. A chart in the report titled Personnel Levels to March 26, 1978 shows the US personnel curve, rapid deployment, a sustained peak during intensive search operations, then controlled drawdown as the mission transitions from active recovery to residual monitoring and final cleanup in selected areas. Field measurements stabilize one concern. There is no dense, widespread contamination that would render large areas uninhabitable, but laboratories analyzing recovered debris are finding something more consequential, evidence that some fragments are not just radioactive, but lethally so at close range, and that reactor fuel particles require assumptions and handling procedures different from inert structural debris. February to March 1978. Whiteshell Nuclear Research Establishment, Pinawa, Manitoba. Debris recovered from the field is shipped under strict chain of custody protocols to a controlled nuclear research facility for detailed testing. Canada's official claim under the Liability Convention states the results plainly. Recovered debris was sent to Whiteshell for testing, and results confirmed that highly radioactive and dangerous material had been deposited on Canadian territory. The expectation, hope even, was that debris would mean low-level contamination, activated metal, or structural components with modest activity levels, manageable through routine handling procedures. The operational reality documented in Canada's claim is stark and unambiguous. All but 2 fragments recovered were radioactive, and some fragments located proved to be of lethal radioactivity. Lethal radioactivity is not a vague term. It means external gamma dose rates high enough to deliver a fatal exposure in minutes to hours of close contact. The claim does not provide every measurement, but the phrase itself eliminates any pretense that the debris was benign. The Operation Morning Light Report's laboratory task list provides the technical underpinning. Whiteshell conducts fuel particle analysis on approximately 370 particles, measuring size, weight, and gamma spectra for isotope identification. High-altitude balloon sampling and additional background surveys support estimates of how many particles might remain unrecovered across the footprint. Why does gamma spectrometry matter? It identifies which isotopes are present: fission products like cesium-137 and strontium-90, activation products, and residual uranium. The spectrum tells you whether you are dealing with activated structure, aged fission debris, or reactor fuel forms. Each category has different hazard characteristics, different handling requirements, and different long-term environmental behavior. Beta count rates and particulate size distributions complete the picture. Fuel particles are small, microns to millimeters, and can be inhaled if disturbed, creating internal exposure pathways in addition to external gamma dose. This finding changes cleanup strategy. It is not enough to recover visible fragments. Particulate contamination requires surface surveys, soil sampling, and decisions about acceptable residual activity levels. Laboratory confirmation transforms the response posture from hopeful reassurance to evidence-based management of confirmed hazard. It supports continued recovery operations, justifies costs, and undermines any diplomatic claim that everything burned up harmlessly. Canada now has test results, chain of custody documentation, and quantified hazard data. The next phase is political and legal. Contrast Soviet design intent statements with measured evidence in Canadian custody, and formalize responsibility under international treaty obligations. March to May, 1978. Ottawa and diplomatic channels to Moscow, plus United Nations forums. Documents arrive from the Soviet Union, but they arrive late, and the wording matters because it shapes legal and public accountability. Canada's statement of claim records the sequence. A Soviet note describes the satellite and states it carried a nuclear reactor working on uranium enriched with isotope of uranium-235. Later notes describe a reactor active zone, a beryllium reflector, and critically, a design that provided for total destruction of the reactor's active zone after entry into dense atmospheric layers. The diplomatic claim of destruction conflicts directly with Canadian recovery, operations, and laboratory confirmation. Canada's filing emphasizes not just the physical evidence, but a procedural failure. The Soviet Union did not provide timely and complete replies to urgent questions posed by a senior external affairs official to the Soviet ambassador on 24 January and reiterated in subsequent communications. Documented individuals appear where the record allows. The claim cites an admission by a Soviet representative, Akademician Fedorov, in a United Nations scientific and technical discussion on 14 February 1978, supporting the conclusion that recovered debris originated from Kosmos 954. Why does beryllium matter in this context? Beryllium is a neutron reflector, a critical reactor component that surrounds the fuel to improve neutron economy and sustain the chain reaction. Its presence in recovered debris indicates that reactor core components, not just peripheral structure, survived re-entry and reached the ground. Beryllium also has specific activation characteristics and toxicity, adding to the hazard profile. Design intent is not an outcome. The Soviet statement that the reactor was designed to be destroyed on re-entry is an engineering aspiration, not a measured result. Actual hazard is established by recovered fragments, laboratory spectrometry, and measured dose rates, physical evidence that does not depend on design claims. These contradictions feed directly into Canada's legal position under the 1972 Convention on International Liability for Damage caused by space objects. The claim argues that emergency response operations were necessary precisely because uncertainty and incomplete disclosure increased public exposure risk and forced broader, more expensive search and cleanup operations than would have been required with full, timely technical cooperation. Once disclosure and responsibility become contested issues, Canada's next step is procedural and predictable. Translate documented measurements, field operations, laboratory work, and logistical costs into a formal claim under treaty-based absolute liability rules. 1978 to 2 April 1981. Ottawa to Moscow, the liability claim and settlement path. The climax number in this story is not a dose rate in Roentgens per hour or an isotope activity in becquerels. It is a cost figure backed by itemized records, documented operations, and treaty law. Canada claims payment in the amount of $6,041,174.70 Canadian. The nuclear satellite is a technological object. The resolution is legal and financial. Canada's statement of claim explicitly ties responsibility to the 1972 Convention on International Liability for Damage caused by space objects. Article 2. A launching state shall be absolutely liable to pay compensation for damage caused by its space object on the surface of the Earth or to aircraft in flight. Absolute liability means no requirement to prove negligence or intent. The event itself, debris deposition on Canadian territory, establishes liability. Canada must demonstrate only that damage occurred and that costs were incurred to mitigate it. The claim breaks costs into phases. Phase 1 covers the immediate emergency response from 24 January to mid-April 1978, aircraft operations, personnel deployment, equipment, field camps, initial recovery, and laboratory analysis. Phase 2 extends through October 1978, covering continued survey work, residual cleanup in town sites, environmental monitoring, and final debris shipment and storage. Why do costs accumulate to this level in a remote footprint? The claim itemizes the reasons. Hundreds of flight hours for fixed-wing aircraft and helicopters, specialist radiation detection equipment, field camp construction and supply in winter conditions, personnel from multiple agencies and countries, transportation of recovered debris to secure laboratories, gamma spectrometry and radiochemistry, packaging and shielded transport, and cleanup operations in populated areas. The claim's framing of damage is broader than physical destruction. It includes the presence of hazardous debris rendering areas temporarily unfit for use, plus the necessity of search, recovery, and cleanup operations to prevent further harm to persons and property. Without measured debris and documented operations, there is no credible path to compensation. The entire response structure, airborne search leading to helicopter verification, leading to ground recovery, leading to laboratory confirmation, leading to cost accounting, becomes the foundation of the legal claim. The settlement, reached in 1981, ends the invoice. But the incident does not end the international conversation about risk, responsibility, and how nuclear power sources in space should be managed to prevent recurrence. 1992, United Nations Committee on the Peaceful Uses of Outer Space. More than a decade after Kosmos 954's re-entry, the international community codifies principles that read like a post-incident checklist: safety assessment before launch, risk reduction design requirements, notification protocols, and public protection logic that does not depend on optimism or assurances alone. The contrast is clear in the documentary timeline. Before Kosmos 954, safety for nuclear power sources in space depended heavily on program internal procedures: keep the reactor in orbit, execute disposal maneuvers, rely on design intent. After, safety is also framed as an international governance obligation with explicit objectives, quantified exposure limits, and transparency requirements that acknowledge the potential for failure. The United Nations principles state a safety objective: to protect individuals, populations, and the biosphere against radiological hazards. The text references dose limits such as 1 millisievert per year as a principal public exposure limit in planned situations, a concrete threshold, not a vague aspiration. Nuclear power source is defined as a category that includes reactors and radioisotope systems. Space reactors like the BES-5 are singled out for additional scrutiny because their operational inventory and potential re-entry hazard are greater than radioisotope thermoelectric generators. These principles are not technical schematics. They are risk governance frameworks, how states should plan missions, assess probabilistic risks, design for safe disposal or re-entry, communicate with other nations, and respond if something goes wrong. Kosmos 954 becomes a reference case demonstrating that no casualties is not the same as no consequences. The cleanup grid spanning 124,000 square kilometers, the laboratory chain of custody, the diplomatic dispute over disclosure, and the $6 million claim show why norms must address the full life cycle: launch, operation, end of life, and potential failure modes. The final documented lesson is operational, not rhetorical. If a reactor cannot be guaranteed to stay in orbit under all credible failure scenarios, the containment system is not the reactor vessel or the disposal orbit. It is the emergency response plan, international cooperation agreements, and liability mechanisms that activate when the reactor comes back to Earth. A satellite designed to keep radiological risk in space forced governments to write procedures for managing risk on the ground, measured in square kilometers, in Roentgens per hour, in treaty articles, and in the currency of accountability.